is that we have written down all the rules. We know the rules here, and we know the language, and we know the read and write symbols and everything. Then we just look at the symbols and we try to translate it according to states. We say, okay, in S0 it reads this, in S0 it reads it. We write the symbol here that we state we're in, and the head is on what? That's what we write. And based on that, we will know this machine will basically keep changing states, and it will make the 0 in the middle as 1 and then go back. So basically what's happening is that, imagine there are 1 1 0 1 1 1. Now in unary we know this is 2 and this is 3, right? But if we do unary addition, we can just, if any number is separated by a 0, we can just add it by removing the 0 and putting a 1 there. Then this becomes, in unary it becomes addition. You basically concatenated the whole string, like both two. This is the way you can add the number of ones to say, okay, these are 5 ones instead of 3 plus 2 is 5, so you just add 1 instead of it. And that's what this machine is doing. And anything that is, so we know what the machine is doing, and we also show it in each step. A Turing machine with a one-way infinite tape has left and on the tape beyond with is not allowed. Explain the difference ordinary Turing machine and Turing machine with one-way tape. Of course, ordinary Turing machine can go both ways infinite, and with one tape it can only go one time. And describe how the left end of the tape can be marked. The left end of the tape can be marked by a diamond symbol. And explain how an ordinary Turing machine can be simulated by one. We can make space on the right hand side, just like we said here. We can make space on the right hand side, and then we can put the new characters on the right, because the right is infinite. Justify why both models have the same computational power. They have same computational power because all problems can be solved by the ordinary Turing machine, can also be solved by the Turing machine with one-way tape, meaning that there is nothing more. So A is less than B or equal to B, and B is less than equal to A, meaning that no one is powerful than the other, meaning that both should be equal to each other. Now, based on this question, we know that this is encoding that was given to us. For example, these are the encodings that are given to us. We can look at these encodings. These are the rules that we need to follow. This is the general way. What it means that there should be SA, this is this, this is this, then this is the new state, this is this, and this is the direction. And for example, we try to decode it here. We have all of these things here. We have the coding we have the encodings that we have to use, and we have the states that we have to follow. This is the first question, for example. So what we do is that we look at this, we say, okay, this is constant, of course, it's always the same. In the brackets we have to make changes. In SI it says we're reading an S1. So what is the rule for S1? If you read a S1, you say 1, so this one goes in here. So, and then we repeat the constant, and then we read a 1. If you read a 1, then you make 1 1, so you put it here. Then you go OC, you read it from here, the constant. Then what's the next symbol? SI. This one we have to follow, meaning that if you read a S1, what do you do again? You put a 1, reading S1, just like this. We follow this rule. Then OC is a constant, then becomes 1 here. This is our helping guide to see. Then 1 is 1 1, and then OC, and then R is and then we have a D, which is R in our case, and R is what is R is 11, and then we repeat the final constant. And this is the same way we solve the question 2 and 3. We know that this is the current state, just like we said. You read the symbol go to the state and write this and change the direction. Then this is the Gödel, and we know that every x has one distinct resulting. For example, 1 goes to unique. So for example, Gödel number is always unique, and every machine can be encoded. So 2 machines cannot have the same Gödel number. That's the thing. 2 machines cannot have the same Gödel number because Gödel number is bijective, meaning that image is decidable and parts of the result are natural and they're valid coding. Mistakes made in creation of rules is not a Gödel number, so random numbers cannot be accepted. So for example, a function C for m and the inverse. Every machine can be made encoding and a Gödel number can be made back to a machine. So YC is injective. We know that no reason to encode. If it cannot be traced back to one machine, why must image be decidable if n is valid encoding of Turing machine? Can't tell apart random number, then you might make strict rules and write rules. If you make rules that don't go anywhere, that makes no sense. Cannot be accepted if made rules were wrong. If you made the wrong rules that go to the wrong thing, then it will not be accepted. O separator, decoding number of O's not included. Why not encoding NC computable? If you can't decode, you can't use. If you can't decode it, then you basically cannot even use it. Why C has to be bijective? No, you can still make Gödel number that doesn't have Turing machine conversion to every number. No need to use all possible numbers. If you have a number and have no rule for it, you can just define some rules and repeat them. So this is a little diagram for injective function and surjective one, that every x has a unique y. Bijective is both. Every y is the result of an x. Nothing on y is empty. So no y is basically empty. Meaning that on universal Turing machine with 3 tapes, what's written on the coding tape? So we have a Gödel number here. We have input here, which is then copied here. This is the working tape, and this is where the working happens, and this is the state. Then whatever the word here is, then is copied here. Whatever we word give it to it. Explain how one step of a universal Turing machine works. So it takes the rules, Turing machine rules, it takes the input, it's read the state, read character, look for S1 in the Gödel number, read transaction, write new character, and move head. So it goes like this, and like this, and like this, and like this. What happens if there are no corresponding transaction in Gödel number? That the Turing machine halts and aborts computation. Then we have some true and false.